Let's take a look now at this simulation, which is in owl space physics. And what I have here is 3 charges. Those vectors that you see there are showing the forces on each charge, the net force acting on each charge. So I have here 2 equal charges, positive. This is positive. This one is positive also. And I put one in the middle. Right? So let's move that one around and see in which direction the forces are acting. So we're going to concentrate on this one, the one that I'm holding and moving around. Okay, just look at the vector force, Coulomb force acting on that charge. So on the right, notice the direction of the force. It's pointing to the right. Now why is that vector pointing to the right when that charge is to the right? So the force due to this charge will be pushing this charge to the right, right? And the force due to this charge will be pushing this charge also to the right. Okay, so both forces are pushing in the same direction, therefore the net force points in that direction. And the closer I get to the force is very strong, and it will go to infinity if the distance between them is 0. But now let's pass to the other side. So now I'm in between them, but I'm to the right of the middle point. I'm to the right of the middle point, which will be somewhere there, right? And the vector there is pointing to the left. Why is that? The force in the middle charge is pointing to the left. So if you're to the right of the middle point, you're closer to this charge than you are to this charge, right? Now the force on this charge, due to the one on the right, points away from it. Let me just draw that. So if you're here, we just said that both forces are pointing away from it, pushing to the right. So that's one force, and then there's the other force, right? Now we're at a point somewhere here. Right? So the force due to the charge on the right is going to be pushing it this way. And the force due to the particle on the left, the one that I drew with blue actually, it's to the right. It's repulsive. But it should be smaller because you're further away from that charge. Right? When you're here, your distance to the blue charge is bigger than when you're here at the distance to the red charge. Right? So this vector is smaller than that one. Therefore, the net force, the net force on that charge is going to be to the left. This is the net force. When you're there. Of course, things would change when you pass the middle point. But right when you reach the middle point, you see no vector force acting in the middle charge, right? That's because the force of one is compensated by the force of the other one. One is pushing to the left, one is pushing to the right. And your equal distances, equal charges, they cancel out. Once you move to the left, now you're closer to, now you're over here. So the repulsive force due to the charge on the left is a big vector. The repulsive force due to the charge on the right is a smaller vector. And therefore your net force is going to be a vector pointing that way. That will be the net force when you are to the left of the middle point. Okay? So to the left of the middle point, your force is pointing that way. To the right of the middle point, the force is pointing in the opposite direction. You see that? When I pass the middle, it's 0. Then it turns to the other side and this way. So if I were to place this particle in the middle, I fix the other two on the left and right, and I place a particle in the middle, the force on that particle will be 0. And if I kick that particle a little bit to the right, what is the force that particle experiences? If I move it to the right, it experiences a restoring force to the left, right? Because you're getting closer to one of the charges. It pushes you away. And if I push it to the left, there is a restoring force pushing it to the right. So what does that tell you about the motion of this particle in between the two charges? What kind of motion it would experience if you were to hit it a little bit sideways? It would be what? Simple harmonic motion. That's right. There is a restoring force that if you go to the right, the force tries to bring you to the center. If you go to the left, the force tries to bring you to the center again. So a particle placed in the middle, if you hit a little bit sideways, then it should oscillate. Right? But what if would it stay oscillating for a long time? The answer is no, because any little deviation from the vertical, from the horizontal line, causes this. You see the net force on the particle in the middle is now up. When you move away, higher above the x-axis, the net force acting on that particle goes up, right? So that net force is going to push that particle and make it go away in this direction. So it would oscillate a little bit here, and then it eventually go like this and get lost, right? And if you push it this way, below the x-axis, then the net force is pushing it down, and it makes it go away that way, right? Now I want to make sure that you understand why that force is pointing that way. The net force acting on the middle particle. So say that you're here, that you put the particle here. You can call it test particle if you want. The force due to the particle on the left is going to be repulsive, so it points that way. So along this line, right? Now the net force acting on that charge just the force acting on that charge due to the one on the right points along the line that connects them and in that direction. When you add those two vectors, since we are writing the line that divides them, those two vectors are the same length and they're pointing in opposite directions, right? The x components cancel each other. The y components reinforce each other. So the net force should be pointing in that direction when you're above the x-axis. When you're below the x-axis, then the force coming from that one is going to be pointing in that direction. The force due to the particle on the right is going to be pointing in that direction. And when you add those two vectors, you have a force pointing this way. All right, so that's what you're seeing here. All right. Now let's change the charge of the particles. I have again a set of 3 particles. But now they don't have the same charge. They are all positive, but the magnitude is not the same. The one on the left has a charge, and the one on the right has a different charge. So let's look around with the middle particle and see what's the force on that charge. So if I'm on the right, we already discussed that the vector force points to the right because both particles are pushing away the third particle. This one is being pushed away by that one and the other one, right? When I'm in between, I'm closer to this one, right? The vector force due to this one points to the left. The vector force due to this one on this charge points to the right. But this one is bigger. The repulsive force with the one on the right is bigger. Now let's see if we can find a point where the force on that particle goes to 0. So I'll keep going. I already passed the middle point. And you can see the x and y coordinates, if you can read that. I'm at minus 0.4 right now, 0.45. And here, the electric field seems to be, the force acting on the third particle seems to be 0. Right? So again, notice that that point is not the middle point. So can we figure out what's the ratio of those two charges? Getting the information from the plot that the force is 0 when the location of the particle is minus 0.67 to the left of the middle point. The middle point is x equals 0. So we found that the 0 point, the force equals 0 point, is somewhere here, and that is the location here of that point is minus 0.67. I didn't tell you that the right particle is located at 2 and the left particle is located at minus 2. All right? So I found that this is the point where the force is 0 on that third particle. This is F equals 0. So what does that tell me about the charges? Call this one Q1 and this one Q2. So what is the ratio between Q1 and Q2? I know it's not going to be 1, but how much is it? Can we figure it out from that information? So how do we proceed there? So what we want to do is make the force due to the particle on the left at that location cancel or be equal to the force due to the particle on the right. Right? So let's calculate how much is F1 at that location. So F1 is equal to K, Coulomb's constant, times the charge, times whatever charge I have in the middle. It doesn't really matter how much it is. We just call it Q, divided by the distance between the charge and Q1. How much is that distance? That distance will be 2 minus 0.67, right? That distance here, if you want to call it R1, it's going to go here, R1 squared. Right? So this is going to be equal to K times Q1 times Q divided by, how much is that? 1.33, and that goes squared. Correct? That's F1, so I could draw that vector this way. That's F1. And the other vector is the force, the repulsive force due to the charge on the right. So that is going to have to be a vector of the same magnitude, of course pointing in the opposite direction. So that's F2. So how much is F2? It's K, Q2, Q again, divided by R2. How much is R2? Well, if the zero force point is minus 0.67 to the left of the axis of the origin, then the distance is going to be 2.67, right? So the distance here is 2.67, and that goes squared, right? 2.67 is this distance. That's R2 equal 2.67. This was 1.3. Okay, so now we're ready to calculate the ratio, right? Because now we say that F1 should be equal to F2. So K Q1 Q over 1.33 squared should be equal to K Q2 Q divided by 2.67 squared. Right? K here and here cancels. Q here and here would cancel. And you end up with Q1 over Q2 equals 1.33 divided by 2.67 squared. Is that right? So 1.33 divided by 2.67, that looks pretty close to being half, right? 0.5. So that's 0.5 squared, and that is 0.25. So Q1 is equal to 0.25 Q2. Does that make sense? If the zero force point is there, because Q1, this is Q1, is weaker than Q2, then that point is going to have to be closer to Q1. Correct? So this charge is 4 times as big as this charge, because this distance is half of this distance. Right? If you call this one 2, the distance, then this will be 1. Right? And a ratio of the distance being longer by a factor of 2, when you square it, you end up with a factor of 4. So that longer distance will be compensated by the fact that this charge has to be 4 times as big. Right? So that's how it works.